In this video, we are going to consider two examples in which we are going to apply the properties of the discrete-time Fourier transform. So, the first example, we've got this signal g of n, and we want to find the Fourier transform. So that's a rectangular pulse. We're going to find the Fourier transform of it expanded by a factor of 2. This was the notation that we were using for time expansion. So let me just remind you with what that is. And the mathematical definition of that was this. G2 of n was g of n over 2 if n is a multiple of 2. 0 else. Okay, so let's just first of all see what we're dealing with, and let's make a plot of g expanded by a factor of 2. So this is going to be a plot g2 of n. So 0 is a multiple of 2. So at 0 we have g of 0. So g of 0 is 1. So at 0 we've got 1. And then 1 at 1 is not a multiple of 2, so we're going to put a 0 there. And at 2 is a multiple of 2, so we've got g of 2 over 2, g of 1. G of 1 is 1. And then at 3 is not a multiple of 2, so we've got 0. And then at 4, g of 4 divided by 2 is 2. So we're going to go g of 2, which is 1. So you get the idea. And then these are all going to be zeros from here on out. So you see we've expanded that pulse by putting zeros, 1 0 in between each point. So we can do the same thing for negative n, and you'll see that what we get is something like this. So this is the expanded. We expand a discrete signal by putting zeros in there, in this case 1 0. So that's what we're calling g2 of n. So we want to find the Fourier transform of this guy. So what we'll do is we'll go back to one of those Fourier transform pairs, and we saw that a square pulse had the Fourier transform, right here, g of e to the j omega was equal to the sine of omega times n1 plus 1 half. n1 here is 2, so 2 plus 1 half, that's 5 halves. So I guess I'll just write 5 halves here over the sine of omega divided by 2. Not sim, sine of omega over 2. So this was the square pulse. This was our result from a square pulse with defined by the edge 2. Okay, that's in the table. So now, what is the Fourier transform? I guess we can plot this. Let's make a plot of this guy real quick. So we've got omega here. Here's 0. And if you can put this in your calculator, whatever you want to do there, but you're going to see something like this. Okay, where at 0 we have a maximum 0, so this would actually be 5. Weirdly enough, you can use L'Hopital's rule. You could show that that's 5, and then at pi, this is where this local maximum occurs. Sine, when we put in pi for omega, we actually get 1 there. And so this thing repeats. So this would be minus pi. Notice it's periodic with period 2 pi. It has to be. So this is the Fourier transform of g of n, but that's not what we're asked to find. We're asked to find the Fourier transform of g2 of n, the time expanded. So from the time expansion property, we know that the Fourier transform of this thing here, Fourier transform is g of e to the j2 omega. So we expanded in time, we contract in frequency. So let's plot that to answer the question. So we're going to, so here's w, or not w, excuse me, omega, and we've got something that will look like this. And you say, well, that looks the same. Well, not quite. It's expanded by 2. So what happens is that this is 5 still, and this is not, or it's compressed by 2, excuse me. So this is now pi over 2, and now this is pi. So it's periodic with period pi. And you say, wait a minute, I thought it had to be periodic with period 2 pi. Well, yeah, if it repeats every pi, then it certainly repeats every 2 pi. So this is the Fourier transform that we're looking for. This is the Fourier transform of G2, I guess. Okay, so that's our answer. So we use the time expansion property there. All right, so let's consider now the second example. Find the Fourier transform of x of n. So here we have this signal here, which is alternating between 0 and 1 over a certain time frame. Well, to analyze this guy, let's consider a different signal first. Let's consider a square pulse that looks like this at 0, 1, 1, 1, 1, and yes. So there are a couple ways of doing this problem. I'm just going to give you one. Okay, let's say this is 0, 1, 2, 3, 4. Okay, and let's call this signal. We already used G, we already used X. Let's call this signal Y. All right. Now notice if we take Y and expand it by 2, then we would have something like this up here, starting at 0, right? We'd have 1 and then a 0 and then a 1 and then a 0. So that would be this guy, 1, but then a 0, 1, 0, 1, 0. So that would get the ones. That would cover the ones, right? And then if we took that thing and added 2 times that same thing, but delayed by 1, or shifted to the right by 1, then we would have our signal x of n. So I'll let you think about that for a second. Feel free to pause the video. But again, the claim is take this y of n, expand it by 2, which means you put 1, 0 in between each sample. So now you'd have the ones, 1, 0, 1, 0, 1, 0, 1, 0. Do that again, but multiply it by 2, so now you'd have 2, 0, 2, 0, and then shift it to the right by 1, and then add it back to this guy, and now you have 1, 2, 1, 2, 1, 2, 1, 2, and so on. Okay, so that's the claim. Again, feel free to pause the video if you need to. So we want the transform of this thing. So we know, what do we know? We know that the transform of y of n, we can find the transform of y of n. So y of e to the j omega. Actually, I'm going to give myself some space here. So I'm going to move that over. Y of e to the j omega is a square pulse, or the signal is a square pulse that has been delayed by 2 units. Okay? It's like g of n. It's just delayed by 2 units. So we're going to take g's transform and apply the Timeshift property by 2 units. So g's transform would be e to the minus j2 omega, because we delayed by 2 units, times the sine of 5/2 omega over sine of omega over 2. Okay, so we use there, I'll write it down here, we use the Timeshift property. Actually, I guess I'll write it right here. So this is the Timeshift property that we used. You see, we're using both tables. We're using the common Fourier transform pairs. So we use the fact that we had already calculated the Fourier transform of a square pulse. So that was this. And then we're using the Timeshift property, right? We need to tack on e to the minus j2 omega, changing the phase of it. So now we've got the Fourier transform of this guy. Now we're going to use the time expansion property. And linearity. Okay, linearity allows us to take each piece separately here. So let's consider this piece. What's the Fourier transform of this piece? Well, from the time expansion property, wherever we see an omega, there should be omega over 2. Wherever we see an omega, we're going to put twice omega. Right? That's the time expansion property. Twice omega. So this guy has a transform, and again, we can take piece by piece from linearity. This guy has a transform of e to the minus j4 omega times the sine of 5 omega divided by the sine of omega. That's from this guy, replacing omega with 2 omega. So that's the Fourier transform of that guy. Now plus 2 times the Fourier transform of this thing. Well, we just got the Fourier transform of y2 of n, which is this. Now we're delaying it by 1. So now we're going to use the time shift property again. So this is e to the minus j omega times 1. Then times the Fourier transform of y2, and here's the Fourier transform of y2. So we need e to the minus j 4 omega sine of 5 omega over sine of omega. And so what you could do with that, if you wanted to, you can factor these things out if you wanted to, or you can multiply the two e's to make e to the minus j5 of omega. Okay, but that's the Fourier transform of the second piece, and so that is the Fourier transform of capital X. So there we have it.